Okay, so last class we discussed correlation, the idea that two variables can run kind of with one another. Here, for example, we have positive correlation, where as kids get older, they tend to be taller. We also could have negative correlation, such as you do more exercise, you tend to weigh less. Now what we're going to do is we're going to take that one step farther, and we're going to introduce linear regression. Linear regression describes how much these two variables are connected to each other. It's not merely simply about the tightness of it, though that's going to come into play. But it's also about how, when one variable changes, how much does the other variable change? In other words, we're now going to step a little bit away from correlation. And rather than thinking in terms of all these things tend to be correlated, we're also going to be making a causal claim. We say it's a causal claim because we have to determine one variable as y, the dependent variable, and another variable as x, our independent variable. And the y variable will depend on the x variable. Usually, if we're going to describe it graphically, the x variable is going to be on the x-axis, the y variable is on the y-axis. Age is our independent variable, height is our dependent variable. Height depends on age. It's not the other way around, right? We easily say this, it's not the other way around. It would be reverse causation otherwise. There's no way that age depends on height, that as you get taller, you get older. That wouldn't make sense. Or if somebody has like a disease that causes them to get shorter, they would also get younger, right? That wouldn't make sense. Clearly, this is the case where age causes. Now, your dependent and independent variables are not always so obvious. That's why reverse causation is always something to be concerned about and something to be thinking about. But here in this case, we're trying to use a nice simple case to start us off. It's pretty clear which is our dependent, which is our independent. When we make a regression, we are going to find a line of best fit, is what it's called. It might look something like this. So it's important when we make our regression that this line, these variables that you construct, they all have to be in harmony with one another. You have to be thinking about population adjustment. If one is adjusted for population, then the other ones, if necessary, must be adjusted for population. That's a big one that I see. So sometimes a student will be running a regression and they might be trying to predict like deaths per 1,000 people, but then they have total school spending. And it doesn't really make sense because one is incorporating this rate, this adjustment for population, and the other one is not. And that's going to radically change the regression. Right? Those are fundamentally two different things. You want to have everything adjusted for population. That needs to be. Not all things have to be adjusted for population. Just for a simple fact that it doesn't make sense to. You adjust for population when an increase in the population would inherently and fundamentally increase the variable you're looking at. Obviously, if there are more people in a state, then there's going to be more deaths in the state. But for something like average rainfall or rainfall on an average day, just because there are more people in a state doesn't mean that the rainfall would increase or decrease. It doesn't make sense. Or where the state is geographically, or the size of the state. The states don't get bigger just because more people live in them. Regression analysis, the actual line, might seem a little intimidating when we see the equation that we use for it, the format that we use for it. But I want you to be aware that it's going to be very, very similar to something you've seen before. And that something is y equals mx plus b. You might know y equals mx plus b from maybe an algebra class. But just as a refresher, y, just as before, is our dependent variable. It depends on x. our independent variable. So those are the same. M is our slope. For every additional unit that x increases, if x increases by 1, then y changes by whatever m is. If m is negative, y falls. If m is positive, y increases. B is our y-intercept. Here I sort of made the intercept close to 0, but it could be, all the way up here. It could be all the way down here in the negative area. It depends on the line, depends on the data. Now, while this is a format you're used to, the issue is, as we will discuss later, you can have multiple x's, and so convention kind of changes a little bit. Notation changes a little bit, order changes a little bit, but it's functionally the same thing. We still have y. Let's make it capital just to make it clear. We're going to put the y-intercept in the first, as the first thing, and we're going to call it beta. And we're going to add a subscript 0. Because all of these are actually going to be betas. Similarly, we won't have m, we will have beta 1. That will be, just as before, multiplied by x. And later we might have x sub 1 for one of the variables and x sub 2 for another variables with its own beta, and x sub 3 with its own beta, and x sub 4 with its own beta, etc., etc. We're also going to add in one more thing. So to be clear, this is the line that we're thinking of. It's exactly the same. But technically, there is one more thing. So I made 2 changes. First, I added a hat here. That y hat means it's the estimated line. So this is literally the red line. This equation here, the lower one, is exactly the same. There is no y hat because we're not estimating it. We're actually describing the individual points. That's what that subscript I means. I stands for the ith observation. As in the first observation, the second observation, the third observation, the fourth observation, and so forth. It's just a notation, little detail. We also have an I there. Just to indicate that one particular x value is matched with one particular y value. One particular first individual has a particular age and a particular height. The second individual has a particular age and a particular height. The third individual has a particular age and a particular height. The really interesting part, though, is that last one. The residual, also known as the error term. So here we have our regression line. I decided to do purple. I thought purple was more clearly visible, bolder. This is the line that we estimate, that purple line. The black dots are the actual observations. Each observation is an ith observation. To sort of give you an idea of what's going on, let's imagine I'm going to add in a blue line, and this blue line will represent the average of all of these heights, all of these observations. Let's pretend that's a straight line. Let's imagine that you knew that I had a young child. I have two. And I asked you, how tall do you think my kid is? Without knowing how old my kid is, or how old my oldest is, we'll say my oldest, how old my oldest is, then your best guess as to his height is the average of the whole, of that range of young kids, whether we're talking like starting at maybe 0 and going all the way out to, 8, or 10 or whatever you call a young kid. That would be your best guess. But then I told you that he was, say, 4. Knowing his age, you get a better idea of his height. Knowing his age, you get a better idea of his height. If I told you that he was, say, 8 or 10, you get a different idea of his height. That estimation of what you think his height is based on age is our purple line. So our blue line is not knowing anything. Our purple line is knowing a little bit, knowing our independent variable. That's what this represents. That's our estimated value right here. Our y hat. This part is our residual. This is the additional part that we can't explain. Like, look, there are things besides age that determine someone's height. Diet, exercise, genetics. These things can't be explained by, my kid is really tall for his age. He's tall not just because he's 4, he's tall because he has my and my wife's genes, and we're tall people, and he eats a lot. Mostly it's peanut butter sandwiches. But he might be this observation. This distance between what we predict, the purple line, and what we actually see, the observation, is the residual. I'm going to make a side note here to remind you that sometimes the residual is called the error term. I don't like that terminology though, because error seems like someone did something wrong. No one necessarily did anything wrong. It has nothing to do with someone making a mistake. It's not that kind of error. It's best to think of it as residual, something that's left over. Like, we figured out this one. You only knew this, you only knew blue. You figured out this much, but there's still this stuff we can't explain. That vertical distance between what we predict and what we observe. This observation right here, I covered up, but this is an observation right here that's directly on the line. There's no residual there. We predicted it would be a certain, this person would be a certain height. They are a certain height, the end. We predicted this person was a certain height, but they're below the certain height. That's the residual. That residual is negative. This residual is positive. Anything above the line will have a positive residual. Any observations below the line will have a negative residual, and any observations on the line have a residual of 0. What is predicted equals what is observed. This is why we have a subscript I, because that I is now talking about individual observations. It's not really trying to predict what we might think will happen or what we would expect to happen, which is useful. This equation represents what is actually happening. Granted, you can use both of them for a line. The only difference between this and the predicted value is you technically get rid of the I values and you drop the epsilon. You drop the epsilon. But that's why there is a subscript. Because not only does each observation have a particular age, and each observation have a corresponding height, but each observation also has its own residual. Each observation has its own residual, positive, negative, and occasionally 0. Mathematically, a residual is the difference between what we observe and what we predict. Each observation has an observed value, but it also has a predicted value. A predicted value based on the independent variable. When we draw that line of best fit, mathematically, what it is doing is it is minimizing these residuals squared and then summed. And we call this the residual sum of squares. Take a moment and appreciate what that means. Let's imagine that line I drew is the line of best fit. If I were to take all those individual residuals, square those values, and no, by squaring them, none of them will be negative anymore. Square those values, add them all up and get a particular RSS. Any other line I draw, and I do that same thing, will have a higher RSS. A regression line minimizes this value, this residual sum of squares. That is why we call it least square regression. That is why we call it least squares regression. It's also sometimes called ordinary least squares, or OLS. Well, we can just call it least square regressions. It minimizes RSS. If you're feeling a bit overwhelmed by this, don't worry, because you will never, ever, ever calculate a line of best fit by hand. Excel has that built in. No one in practice ever calculates this by hand. It's too hard. It would be too time consuming, right? There's an equation for it. It's really annoying to go through. What you have to know, one of the things you have to know, is the familiar intuition behind y equals mx plus b. The math, the algebra doesn't change at all when we're doing least squared regression. Like, let's suppose that our equation is height equals 80 centimeters plus 6 age. I could put in the epsilon, I could put in the residual, I should say, the epsilon at the end. Again, sometimes I do, sometimes I don't. The difference in practice, when you're estimating, you just kind of ignore it. I sometimes put it in just so you can get used to seeing it. Like I do in the lecture notes, I'll put it in when I don't really need to, just because I want you to be used to seeing the epsilon and starting to get familiar that it's always there in that background. You don't always need to put it in for purposes that we'll be working with. Now, if we remember that, I'll make this a little clearer. Here I'm not going to put it in because I don't have the room. If age increases by 1, how much does height increase? Well, it's exactly the same as what you would ask up here. If x increases by 1, how much does y increase? It's m. And remember, m is the same thing as our beta, which is 6. Note that we don't use b at all. We don't use the 80 at all. We don't use the y-intercept at all. And when we're trying to estimate a change, mathematically, it'll just cancel out. If we're trying to estimate that value, and we're trying to get a y-hat, if age equals 8, how tall do you expect someone to be? Well, 8 times 6 is 48. 48 plus 80 is 128. We estimate that for every year this child ages, they get 6 centimeters taller. And if they are 8 years old, if a child is 8 years old, we would expect them to be 128 centimeters tall. Now, granted, there's going to be some complexity to this. We'll talk a little bit later. Like, that means that according to this, if the age is 0, the kid is 80 centimeters tall, which is a really big newborn. So there's some non-linearity to this that kind of throws it off. And in practice, when you look at the growth curve, this is the CDC growth curve that was basing this off of. It is not a straight line. It looks kind of straight, but it's not actually straight. And for the record, it only goes down to 2 years. It's going to look very different. They grow a lot in their first 2 years. They grow a lot in their first year. Hell, they grow a lot in their first 6 months. And then, of course, if we go to very high ages, like we talked about before, when we talked about correlation, right? Things really level off in the teenage years. These individual lines, by the way, are percentiles. So the 50th percentile is our median. 75th percentile is this person is going to be taller than 75% of the population and shorter than 25%, etc. My son is almost 5. My oldest son is almost 5, and he is 2 inches shy of 4 feet. These is inches right here, so he's about 46 inches. So you can get it right about here. He's not even quite 5 yet. He's kind of more over here. He's a very tall child. Let's switch over to Excel. So, we'll go to our website. We're going to pull up data set 5.
Hey, David?
Yeah? What?
Do you have any confirmation that your students are watching these?
Well, they better be. We'll find out when they take the test.
Like, are you putting them on YouTube?
Yeah, I put them on YouTube, and then I link to them in Blackboard.
So can you see the number of views on YouTube?
Yeah, I can.
So
I haven't checked.
Them?
Yeah. It's from my online course.
So
they
cute.
are.
Look at you. I love you so much.
Okay, that's great, honey.
Okay.
This is data taken from Rate My Professor website on January 17th, 2014. Montgomery College professors with at least 25 ratings. So I just had started Montgomery College, so I'm not here. But we do still have a fair number of observations. We have over 200 observations. We have their department, which is nice. Also have the total ratings, of course. We have their average quality, how good students thought they were at teaching. We have their difficulty, how hard the class was. We also have something they thankfully no longer record, but it's helpful for all purposes if students thought that the professor was hot or not. And hot means they thought the professor was physically attractive. So we now can ask this interesting question, right? People say that, oh, you get better ratings if you are, if the professor gets better ratings if they are easy, and they get worse ratings if they are difficult. So a professor can make their Rate My Professor ratings go up if they're super easy. But then there's this question of how much do they go up? Like, we could check a correlation. Yeah, we can do that right now if you want. Correlation all the way down here. Keep going, comma. Make sure to hit that comma so that it tells you a different argument. Go all the way up to this one. And yeah, we do indeed find a very strong correlation. As one variable goes up, the other variables goes down. So it's this very clear negative correlation. But we might be curious as to why. As to how much, I should say. We might be curious as to how much. When the difficulty increases by 1 point, quality falls. How much does it fall? So that's a question of regression. First, though, let's recognize that we are going to establish a causation. We are going to say that difficulty causes quality. We are not saying quality causes difficulty. that would be a different regression entirely. We'll talk about that later. But we are going to say difficulty causes quality. Let's get rid of this. So we're going to go into data analysis. We are going to go to regression. We are going to now declare our y variable. Our y variable is quality, and we're going to make sure that we include the title quality in the regression. That first line. X is our difficulty, so we'll highlight that. Now we're going to hit labels in first row. Labels, or just this labels option. This option tells Excel that the first row of our data is a label. And therefore not something we should consider an observation. Make sure that you hit that button and make sure that you've included labels in your ranges. I've seen students who don't include the labels in their ranges, so they would start this in D3 or E3, but they do hit the labels button, and so then Excel thinks that 3 and 4.5 is are your labels, or what you're calling these, rather than actual observations. So make sure that's harmonized. You can, if you want to, you can click the residuals. It will tell you the residuals for all observations. We don't have to do that yet. These other things you don't have to necessarily worry about, but you do have to worry about this output range. This will tell us where it's going to output the results, just like we saw with the correlation table. So I like to hit output range because I wanted to have it on the same worksheet ply, and I want to select that. I'm just going to select somewhere for the upper left-hand corner of this table it's going to generate to be. I'll pick I3 because sure, that seems fine. Doesn't really matter as long as there's a lot of blank space right here in this area. And hit OK. And then it runs regression. Does it super fast. Super, super fast. Because it's a computer, that's what it's good at. This area right here, we're going to talk about. This area we're going to talk about later. Here you can see under this ANOVA analysis. ANOVA stands for analysis of variance. We'll be talking things about the FSTAT and significance F later. But note that residual SS stands for sum of squares. Residual sum of squares is 67. So if we were to draw any other line and run the numbers and calculate all those residuals and square all of them and then sum them all up, we would get a result greater than 67.07578. This, by the way, is the regression sum of squares. Sometimes I call it the explained sum of squares to give it a different acronym. And that is the difference between the average and our predicted. We can talk about that more later. What we care about right now is this last section right here. These are our confidence levels. We can kind of ignore those. Those are sort of the bounds. The two areas we care about are the coefficient and the p-values. The p-values tell us if it is statistically significant or not. It is similar to this t-stat, which is right next to it. Note that these are t-stats, just like t-stats from the last unit, t-stats when we were calculating hypothesis testing. These are exactly the same kind of t-stats. It doesn't take the absolute value, but Excel knows to take the absolute value for determining statistical significance. So the p-value is really what you want to care about. It determines statistical significance. It is the smallest alpha you can claim and still get statistical significance. You could go to the t-stat that it outputs, and it's always going to output it as a t-stat, never a z, because you don't put in a sigma, right? It has to figure out the sigma. It has to figure out the estimation of sigma from the data you provided it. But you can get that 17. You can take the absolute value of it. You can go ahead and then put in various t-stats. we would be basing this off of a degrees of freedom of 209. We don't do 210. 210 is a reference. This reference is for the whole regression. But though we have 211 observations, we don't subtract 1, we subtract 2. We subtract 2 because we have 2 means. We have a mean for the quality, and we have a mean for the quality, and we have a mean for the difficulty. That's 2 means, so we would only have 209 degrees of freedom. Now watch what happens. If I put in t distribution 2t, I'm going to take the absolute value of our t-stat, because if I put in a negative value, it's going to get annoyed because I put in a two-tailed distribution. So it's going to be two-tailed here. And then I put in 209 degrees of freedom. When I do that, I get exactly the same thing. P-values are the lowest alphas you can claim and still have statistical significance. So since our p-value is super small, we know it's statistically significant on our level loads. If you're wondering, David, that doesn't look super small. That's 1.9. That's not super small for a p-value. It's greater than 1. It's huge. No. It is not 1.9. It is point, and then there's like 40 zeros, and then it's 19032. That E that you see is scientific notation. If I have 5.6 E3, then that means it is 1, 2, 3. 5,300. If it is 5.6 E negative 3, then we're moving that decimal place. Then we're moving that decimal point 3 places to the left. 1, 2, 3. Take a look at that one. 1.9 E negative 41. Not near negative 3, negative 41. It is functionally 0. It's not actually 0. It's not literally 0, right? Because, it could be a coincidence. There's just an infinitesimally small chance it is. Right, for our purposes, it's functionally 0, even though we have to be aware it's not mathematically 0. We haven't proved anything. We just have very strong evidence. So we can say the difficulty coefficient is statistically significant. Technically, the intercept coefficient is also statistically significant, but no one really cares because we're really cared about our variable that we put in. These coefficients are beta 0 right here for the intercept and beta 1 for the difficulty. This is our y equals mx plus b line. Oh, one last thing, one thing too before I forget. That p-value that's over there in the group work I assigned in the last unit about the hypothesis testing, I think it was the last question. I asked you to find the lowest, the lowest possible alpha that you can claim and still get statistical significance, or the highest confidence level that you can claim and still get statistical significance. I was asking you to calculate your the p-value essentially. So that was just a preview if you saw how I did that, or if you were able to get that far, where you saw in the answer key how that was done. That's what was going on. That was my way of trying to familiarize you with this step right here. So immediately we have an answer to our question from the beginning. If someone becomes more difficult, we know that their quality will fall, but we didn't know how much it would fall. Well, now we do. It falls by about negative 0.86. Almost a full point. Now, granted, you can't get negative 0.86 because everything's in tenths, right? So you can get, 0.8, you can get 0.9, but that still gives us really interesting information. The lumpiness of it is there's going to be imperfections. For every additional level point of difficulty a professor gets, then their quality rating falls by 0.86. What's also neat is that we can estimate how good a professor is based on this. So, for example, let's imagine someone had a difficulty of 3, a moderately difficult professor. Well, what would we expect their quality to be? We would take the intercept, add in the coefficient times 3, and we get about 3.6. We'd expect a professor to have about 3.6 for their quality. Now, I should mention before I go further, there are problems with this data. Like, it's bounded for 1. You can't get more than 5. You can't get less than 1. And they are averages of a bunch of data with those bounds. So doing some kind of regression analysis isn't terribly appropriate here, but I like this data because it's very clear. You know, a lot of you use rate by professor, so you have a good intuition of what this is, and you can see what's going on in an interesting way. What's neat too, and again, you technically shouldn't do this because of the problems with regression, but if we set that aside, we can also use this to evaluate professors. You know, some professors have very high quality ratings. Are they high because they're easy, or are they high because they're good? You know, maybe somebody has a really high quality rating, but given how hard they are or how easy they are, that quality rating isn't that high. Meanwhile, someone might have a really low quality rating, but maybe given how difficult they are, it's not actually that low. Remember we said the residual is the stuff we cannot explain? It also is the stuff we can't observe. And it's hard to observe pure quality, especially when you have this if you're easier, people like you more, and therefore the quality rating goes up issue. In other words, one way we can evaluate how good a professor is by looking at the residual. I'm going to actually expand this a little bit just so you can see the steps. I'm going to do an insert. I'm going to put in the predicted value, and then I'm going to add in the residual. There you go. So the predicted quality is going to be equal to our intercept plus, and note I'm saying plus even though this is a negative number, because if I say minus and then I click it, then it's going to be minus and minus, and it's going to add. So just you always use plus, and then you let the negative values do the work. Plus that coefficient times whatever somebody's difficulty is. And we're of course going to have to lock these cell references, because we're going to want to do this for everybody. So for example, given how hard my colleague, Professor Leonard, is, right, difficulty of 4.5, their quality, while it seems like they're only mediocre, is actually quite above what you would predict. It's actually, based on this, he's quite good. Again, it's flawed, so I don't want to read too much into it, but just based on this, he's quite good. We can then take the residual, which is equal to what we observe minus what we predict. And let's just do that with everyone. Now, we can find according to this analysis, again, flawed analysis, but still an interesting analysis, the best professor at Montgomery College, they're going to sort and just sorting based on residual from largest to smallest. Someone in the science department has a residual of 1.3. They are more than a full point higher than what you would expect. And then you can go the other side and you can find people who are just right on the line. The residual is just right there. It's right exactly what we would expect it to be, more or less. I'm rounding, obviously. And then we get into people who are lower than we would expect. Right? You are so easy, but people still don't like you. What does that say? If you sum all these residuals, you'll always get 0. Not just about 0, not just around 0, exactly 0. By the way that regression analysis works, it's always just going to actually exactly equal 0. So what this tells us then is that not all residuals can be positive, not all residuals can be negative, and we're going to unpack that theme a little bit more when we sort of dissect the assumptions of regression analysis next class.